So we're now going to revisit an example we looked at in the previous film, and we're now going to use the corollary of Fermat's theorem to optimize it. So the example we revisit is f of x is equal to x to the third minus 3x plus 1 with domain minus 2 to 3. Now, what does the corollary of Fermat's theorem say? Well, it says that if f defined on, let's say, AB, and C in AB is local extreme point, then one of the following three has to happen. C is either endpoint, stationary point, or singular point. So being an endpoint means that C is equal to one of those two guys. Being a stationary point means that the derivative is 0. Being a singular point means that the derivative does not exist. Now, notice here, in the way I formulate it in a closed interval, but I don't require f to be continuous or anything. But this thing here, so notice that f is polynomial, which implies that f is continuous and differentiable on minus 2 to 3. What does that give us? Well, this tells us where the extreme points can be. And now we can use the Min Max Theorem, which says that if f is continuous on some interval ab, this implies that f has global max and min. What does this tell us? Well, this tells us first of all that this function has a global max and a global minimum, since every global max and global minimum points are also local max and local minimum points. This corollary here tells us that the global max and global min of f has to appear in this list. That means if I make a list of all such points of my f, then I can just choose the one which gives the largest value for f and know that that's my max, and the one that has the smallest value for f and choose that as my min. So let's do this. Let's make this list. Now, here we can notice that this thing here implies f has no singular points on minus 2 to 3. So we can rule this out. Now the endpoints are minus 2 and 3, so those are easily identifiable. Then what remains is to identify any stationary points. To do this, I have to make the derivative. So I can't avoid this. And here this is equal to this, meaning that this is 0 if and only if x is equal to either plus or minus 1. So now I can make my list here. So I have the endpoint here, I have minus 1, I have plus 1, and I have this endpoint here. I can compute the value of f here. We did that in the last film, but I mean, it's not complicated, but it's minus 1 here, 3 here, minus 1 here, and 19 here. So now since I have here the list of all possibilities, Min Max Theorem tells me that I do have a global max and a global min. I know that this has to be my global max value, and that these two guys here are my global minimum values. So this function can never be larger than this and never be smaller than this. Now, this may not feel like much, but please keep in mind, so there do exist functions that, for instance, so let's say here, if I now change the domain here to R, what would change in this part of the computation? Well, here, this guy is continuous and differentiable on R. He has no singular points on R. My function has these 2 points here as stationary. There I have the value 3 and minus 1. So of course the endpoints are out of the water then, so they don't exist. I took them away. So this list I make only contains these two values. Will this then be my global maximum and global minimum? No, because this thing here is now out of play because I no longer have a closed and finite interval. So I'm no longer guaranteed the existence of a global max and a global minimum. And in fact, if we draw this function, it will look something like this, and this, and this. So here I have my 3, here I have my minus 1, and then I go up to infinity and down to minus infinity. So this is a local max, but not a global max. This is a local min, but not a global min. And in fact, the function, when I change the domain here, ceases to have global maximum and global minimum points. And the beauty of using these two in combination is that this list you get, you're guaranteed that here your global max and global minimum points are without having to make any other considerations. So once this thing here vanishes, you have to be careful. I mean, you could have a function that looks like this, right? That has stationary points here and then has a behavior such as this. So then this would be a global max. This would be a global min, because here you'll have an asymptote going to 0, say, and here you'll have an asymptote going to 0, or, well, I don't know, 0.1 or minus 0.1. Nobody cares. But this guy does have an absolute maximum and absolute minimum, even if it's defined on R, and has the same thing here. So basically, if the min-max theorem is out of play because you're not continuous on a closed and bounded interval, you need to take, let's say, asymptotes into consideration. So things become more complicated. So this is a simplifying feature.